energy problems. I think there are probably 4, maybe 5 questions that are conservation of energy. One will look a lot like this, where I have an object that starts at a point, either at rest or not at rest, and then moves through the path, and you have to figure out the speed or the position at different points. So for example, here on number 3, really the first step that you do is to answer the question, does this object have potential or kinetic energy or both at these different positions? In fact, I have a question like that in the exam. What kind of energy does this object have at point A, B, or C? That's the very first question that you'll see. And so at point A, this object has potential energy. I know it has potential energy because it's at a certain height, it's not at ground level. And then I know it doesn't have kinetic energy. The reason I know it doesn't have kinetic energy is because it says it's at rest. So if H is 0, potential energy is 0. If V is 0, kinetic energy is 0. And then I want to know what is the velocity at point C. And so at point C, it has potential energy, and it also has kinetic energy. It's at a point lower than here, so some of this potential energy is moved into kinetic energy. So I know that this object has some velocity here. So what I do is I set this energy equal to that energy. That is the conservation of energy. And the total amount of energy is constant throughout the path. So it's a mgh. That's the potential energy. In fact, I'm going to go and do a 5 here. Equals mg2 plus 1/2 mv squared. And then I can cancel out the m's, divide through all the terms by m, and I get 50 minus 20 equals 1/2 v squared. That's 30, 60. V is equal to the square root of 60, or 7.75. You'll have several questions like that, where you have to figure out the position or the velocity of an object at a different point. Okay? Make sure you can do that. Y'all can do that, I think, right? All right, that should be sort of the very first thing you can do. You'll have spring questions as well. Let's see here. Oh, like number 10. Number 10 is a conservation of energy problem where you have to figure out the velocity of the object right after it leaves the gun. Listen, one of the hard things on this exam, I think, is that not all the questions have figures. I know that a lot of you like figures. I do too. They really help me to think about the problem and approach it. So you need to get good at reading the problem and then drawing what is the situation. So I think that's useful here to draw a picture that represents what's going on. So in my initial state, I have it that looks like this. I know that my compression is 0.03 meters, and so the potential energy is equal to 1/2 times k times x squared. And then in the final state, this spring has stretched out to x equals 0, and the ball is now traveling with some velocity v. And so now this object has a kinetic energy equal to 1/2 mv squared. I know that some of you think, well, this stuff is going on in my head, but sometimes when it goes on in your head, it gets all jumbled up. So I really recommend that you draw a picture. You should have time to draw a picture. If you know how to do this work, you should have plenty of time to draw pictures. And that'll help you to think about how to approach the problem. So here, I say the potential energy is 1/2 kx squared, and then that's equal to 1/2 mv squared. My masses don't cancel here. Anytime you have a spring, remember that because I don't have a mass term in the kinetic energy, then the mass isn't going to cancel from the potential energy. But I can get rid of those 1/2s. I'm looking here for the speed. So v is kx squared over m. Square root of that. That's the square root of k, which is 250, times x squared, that's 0.03 squared, divided by m, which is 0.02 kilograms. And then that answer is, I don't know, does anybody know what that is right off? 3.4. making sure that you do the square root of this entire operation right here, not just the top, that it includes the denominator too. Okay, you'll have a question like that. That's an elastic potential energy problem. You'll have questions about work, like for example, this one right here, we're trying to find the work done by the man on the block. You'll have, I think actually it did do some units problems like this, so make sure you're reviewing your SI units. Anytime I ask you what the SI units are for something, like for example here in the case of work, you would say work is equal to force times displacement. And I know that force is equal to mass times acceleration times displacement. So just break down your equation to its most basic forms, and then put in the units for each of these. Kilograms, meters per second squared, meters, and so the answer would be kilogram meter squared per second squared. That's true for energy. You would start with, say, 1/2 mv squared, and do m as kilograms, v is meters per second squared, so meters squared per second squared. That's true for power and energy over time. Just go to those basic equations and then put in the units for each variable. If I ask you for the basic SI units, don't try to memorize them is what I'm saying. Go to the equations, which I'll provide for you, and find the units. All right, we're going to do some momentum here. I know that y'all are probably most interested in this, right? Because that's what our quiz is on today. So let's look at number 21 here. I like this one because, like I said, it's all words. There's no picture. You'll have some questions with pictures too, but I like for you to be able to read this and to create a figure out of it. I have a mass of 11 kilograms, M1. It's moving 2 meters per second to the right. Mass M2 is initially at rest. They have an elastic collision, and they bounce off with a velocity. The M1 bounces with a velocity to the left. So my figure is going to look like this. M1 is moving to the right with 2 meters per second. M2 is at rest. Then M1 has 1 meter per second to the left. And I want to know what M2 is. All right, so I'd say M1 times 2, that's 11 times 2 plus 0 will equal to 11 times -1 plus M2, which was 22 kilograms, times V2. That's 22, 33. So it's going to be 3 halves, or excuse me, 3 halves, 1.5 meters per second. And it came out positive, so that's how the sign is important there. Be able to do a problem like that, it's just like the problem that we've been doing, where I show you the picture of the ball and the timeline and move off in the direction. But make sure that you can do it without a picture too. Tell me. Positive means to the right. Huh? Positive means to the right. Right, yeah, positive means to the right. Yeah, and negative means to the left. Just like in our XY coordinates. Alrighty? I do want to just talk about this just for a minute. This was in the notes, but we didn't talk about it in class. Elastic. In collisions, we have elastic collisions and we have inelastic collisions. Elastic collisions conserve what? Do you remember? They conserve energy, right? Elastic collisions conserve energy, and what else? And momentum. Right, linear momentum. All collisions conserve momentum, but elastic collisions also conserve energy. And then inelastic collisions conserve just momentum. Most collisions in the universe, like if you bump into somebody out the hallway, or if you have a car accident, that is an inelastic collision. Because in a car accident, you lose all sorts of energy, right? Energy goes into the car to deform the metal or the plastic. You have the thermal energy that's released. You have sound energy. But momentum is still conserved. Energy, not conserved. Momentum is conserved. I remember that sounds bouncy, right? When something's elastic, it's really bouncy. But if you have a really bouncy object, it conserves most of its energy. There aren't any truly elastic collisions in the universe. One good one is the collisions between atoms. Because atoms don't actually touch when they interact with one another. They'll come close to one another, and then they'll collide via their field forces, right? Electric or gravitational forces. And when that happens, since they don't touch, they don't lose any energy. So that's an elastic collision. Another elastic collision that we approximate them as elastic are things that just don't lose much energy. Like billiard balls, when they bounce off one another, they don't lose very much energy. We can say those are elastic, even though they're not really. Okay? Know what elastic and inelastic is. I'll ask you that. Are there any particular questions you'd like me to address?
Tornado question.
What's that?
There's a question about tornadoes.
Oh, so that's chapter 7. There's no chapter 7 on the exam. All right? No chapter 7. Make sure that you understand impulse. Like here, number 24. What is the impulse for a 2 kilogram mass that goes from -4 to +3? So impulse, I, is equal to delta P. And so that's going to be m times delta v. Usually it's the speed that changes, not the mass. That doesn't always happen. This is 2 kilograms times VF minus VF minus V initial. That's going to be 3 minus -4, or 2 times 7, or 14. All right? You'll have other Newton's second law problems. Well, this is a good one. For how long should a force of 100 newtons be applied to an object to change its speed from 20 to 30? Anytime I see forces involved, think Newton's second law, but think it in terms of momentum, that F is equal to delta P over delta T. If I have a change in momentum, that means that I've had a force acting on that object. And here I'm looking for how long does that force have to act. So I say delta T is equal to delta P divided by my force. So I have a force of 100 newtons. I have a momentum of a momentum change of 25, that's my mass, times VF minus VI, 30 minus 20. That's 250 over 100, or 2.5 seconds. You'll see problems like that on these Newton's second law problems. On these Newton's second law problems, make sure that you recognize. I know that sometimes I say you add those velocities together, but here we took the difference in the velocities. The reason that's the case is because here the object didn't change direction. When it changes direction, that's when you get that interaction of the signs, the minus and negative number, where you're adding the numbers together. Got it? Chapter 7, man. No chapter 7. No chapter 7. No rotation at all. Okay? All right. So, yeah, number 20. Good question. And it's a good question. It's one of these where, it really helps you to draw the picture for this. By the way, on the Moodle page, make sure that you're not neglecting these concept tests. Download 5 and 6 and look through those. You'll see that a lot of the conceptual questions actually come from these. Some of them don't. Some of them are different. But a lot of them do come from that. So that's a great way to study the conceptual questions, is to download those concept tests and practice them. They're in the back of your book, too. They're not the answers. The answers are on these. Okay, so I say that because there's a couple questions like that, like number 20 here in those concept tests. So I have a person with a mass of 60 kilograms standing still. So my initial is a person that has an object, say a medicine ball or whatever, and then they throw it. So that's the initial the final state looks like this. Person, the ball is now going in that direction, and I want to know what is the speed of the person. So presumably, this person will now go in this direction. Here, both of these have velocity equal to 0, so the momentum is equal to 0. But down here, the speed of this ball is 10 meters per second, and I want to know what is the speed of the person. So the initial or the final momentum also has to equal 0 here, because whatever momentum I start with in the initial, I have to have in the final state. That's the conservation of momentum, that pi is equal to pf. So I say pi is equal to pf. 0 equals the mass of the person, 60 times vf, plus the mass of the ball, which is 3 times v times 10. All right, so in order for that to be 0, vf has to equal to negative or a half. It's actually negative a half, but since it's asking for the speed, then I just look for the magnitude of that. Okay? Make sure you understand the different quantities and what they are. That you know what a vector and a scalar quantity is. Like vector has magnitude and direction. A scalar quantity only has direction. So momentum, vector or scalar? It's a vector. Very good. Energy, vector or scalar? Scalar, right. There's a question on the exam from Wednesday about vectors and scalars. Just make sure you understand that you remember what your other vectors and scalars are. Force, vector, scalar. It's a vector. Let me remind you of the vectors. So force, velocity, acceleration, displacement, those are all vectors. Scalar quantities include time, mass, distance, speed. Like we have the scalar quantities for the vectors. Distance, speed. We don't have a scalar acceleration. Displacement is a vector quantity. It has a direction. Okay? Just remember those different things. All right. What else on here? Should you remember power? Here's another question. This is a conservation momentum problem, but where you have to actually draw, it helps you to draw the picture. Any particular questions from you folks? We definitely have a question like this where I give you a picture. I think those are easier. Remember this. So number 25, a student asked about this earlier. If you look back in the conceptual questions, these sort of questions come up there in the concept test. You have a particle of mass m and you double its momentum. How have you changed its kinetic energy? Remember, momentum is mass times velocity. Kinetic energy is 1/2 mv squared. So if I double an object's momentum, what does that mean I had to do to the speed of that object? I had to double it, right? So if I double the momentum, that means that I doubled the speed. Or I could have doubled the mass, but it says that it's a mass m, so that's not changing. And so if I double the speed, what do I do to the kinetic energy? I quadruple it, right? Because I have this quadratic term, because v is squared, if I double v, I quadruple the kinetic energy. So here, the answer would be D. All right, you'll have some questions like this where looking at F equal delta P over delta T. Delta P over delta T is equivalent to the force, right? That's just straight from Newton's second law. This is on the equation sheet too, by the way, so you'll be able to see it there. But here, a rubber mat will decrease the force of impact if an object falls onto it. Why does a rubber mat decrease the force? What does the rubber mat actually do to decrease the force? That's right. It makes it, it just slows it down so it increases that time. So the delta T gets bigger And if delta t gets bigger, then f gets smaller. So here, the time of the collision is increased. Okay?
We have clockwise,
No. I know, I'm sorry. I know that you've been studying that really hard on the weekend. I hate to pull that chapter 7 out of this test, but
no, I think actually let's study this. I didn't realize it was chapter 6 and chapter 7.
that's okay. All right. All right. What other questions we got? Particular questions about the exam or the quiz?
Like having this division specific to.
Yeah, that's a good question. Let's look at that. So, well, I remember the question. Let's just. So when I have an object, whether it's moving or not, so if I have an object, say it's moving through space, and then it splits up for some reason, this object has a certain momentum, right? That's equal to the mass times its velocity. And if this object splits into 3 pieces, so now you have 3 pieces that are moving, say like this, it still has the same momentum. So whatever momentum it has over here, the sum of the momenta of these 3 objects still have to be the same. And they do. They will still be the same. And that was true. We had a question about a uranium nucleus. So a uranium nucleus is sitting there at rest. So P is equal to 0. And then it breaks into 2 pieces, one big and one small. The big one goes in this direction, and the small one goes in this direction, but such that the momentum is still equal to 0. That is, that the momentum of this object is equal to the momentum of this object, but opposite. This one's positive, this one's negative. What can you tell me about the speeds of these 2 objects? If they have the same momentum, which one has the bigger speed? The lighter one, right, because P is equal to mv. If this is constant, if m is big, that means v is small. So this has the small v, it's slow, and this has the big V. It's really fast. Right? I mean, you thump a speaker and it doesn't do hardly anything, but if I thump a piece of paper, it goes a lot faster. I impart the same force, so I get the same change in momentum, but one has a bigger mass, so it goes at a bigger speed. All right? Other questions? We still have a couple minutes. Yeah. On this exam? Yeah. Okay, good. Whenever you have something that sticks together, that's called a perfectly inelastic collision. You don't need to know that, but I might call it that in the exam, but I'll draw a picture. I don't expect you to know that. But this is called a perfectly inelastic because it sticks together. When they stick together, that means that their masses are combined. So I have a 4 kilogram mass and a 1 kilogram mass that have initial momentum. The initial momentum is equal to 30 minus 20. And so that's equal to 10 kilogram meters per second. I just added up these 2 numbers. That's their initial momentum. And then these 2 objects, they stick together. So the 2 objects have a combined mass of 4 plus 1, or 5 kilograms. And the 2 objects have a momentum equal to 10 kilogram meters per second. And now I want to know what is the speed. So I say P is equal to m times v. 10 is equal to 5 times v. So v is 2. So I have 2 objects. Let me draw a picture. I don't know that you need a picture on this, but let me just draw it. The 4 kilogram mass is in this direction. The 1 kilogram mass is in that direction. Then they stick together, and they make one big object, and they can move off at a speed of 2 meters per second. Okay? Yeah, Jonah?
And one I seen was maybe M1 V1
Uh-huh.
And one, and they add the V3 for the velocity of the two together. Is that viable? As a V3?
Oh, yeah, it was just, was that something that I done or something?
Oh, no,
Yeah, it's just a third velocity. So what he's saying is that, you're still saying the initial and the final, but we'll have two objects here. We would call this V1, V2, and then you have a big object and say it's moving off in this direction at V3. That's what you're saying, right? Yeah, that's okay, as long as you're still setting the momentum here equal to the momentum here. Doesn't really matter what you call those variables. All right. Okay, we need to get started on quiz. So I will hand it out, and then I'll start the clicker base. Listen, you'll have 20 minutes, but I want you to hang out until those 20 minutes are up. I don't think it will take you 20 minutes, but if you want to look on your phone or whatever, just raise your hand. Stay in your seat. So raise your hand and give me your test, and I'll take it, and you can put your clicker away. You can study or do whatever you want to do. Yeah, anyway. I'll put the equations up.